All right, welcome. Today, we are going to crack the code on a really fascinating puzzle called restricted paths. It's this awesome challenge that weaves together a few classic computer science ideas in a super clever way. So let's just dive right in. So, picture this. You've got a huge, complex maze. Maybe think of it like a network of roads. Our job is to figure out just how many ways there are to get from point A to point B. But of course, there's a catch. There's this one single peculiar rule that changes the entire game. So the real question is, how on earth do you count all the possible routes when your movement is so strangely limited? You know, the first step to solving any puzzle is always the same. You've got to understand the rules of the game. So let's break down the one critical rule that defines this whole challenge. And here it is. The rule is simple. You can only move from where you are to a new spot if that new spot is strictly closer to the finish line. A good way to think about it is like this. You're standing on a mountain, and your destination is way down at the bottom. The rule means you're only allowed to take steps that go downhill. No walking on flat ground, and definitely no going back uphill. Ever. This one little constraint is what makes this whole thing so cool. Okay, so before we jump to the right answer, I think it's really helpful to see why the most common, the go-to algorithms that you might think of first just don't work here. Figuring out the dead ends is honestly half the battle. So what's in our usual toolkit? Well, we could try a brute force search, right? Just check every single possible path. But in a big network, that would literally take forever. It's just way too slow. So, okay, what about a breadth first search, or BFS? BFS is great for finding the path with the fewest steps, but our rule isn't about steps, it's about the total distance. BFS doesn't really care about travel times or waits between points. So yeah, both of our first instincts kind of lead us down the wrong path. And this is where we have our breakthrough. With a lot of tough problems, the solution isn't about more brute force. It's about a single, elegant shift in how you look at it. It's that aha moment that just unlocks the whole thing. So here is the key insight. The rule is all about being closer to the destination. What that really means is, before we can even think about counting paths from the start, we first have to figure out the shortest possible distance from every single point in the entire network to the end. We have to map out the whole terrain before we can even know which steps are actually downhill. With that key insight in our back pocket, we can now assemble our toolkit. We're going to combine two powerful classic algorithms to build a really beautiful and efficient two-part solution. Our first tool is the one, the only, the legendary Dijkstra's algorithm. This is the absolute perfect instrument for our first job, figuring out the shortest path from one point to all the others in a weighted graph. It's exactly what we need to map our terrain. But here's the really clever twist. We don't run Dijkstra's from the start. We actually run it backwards, starting from our destination, node n. By doing this, it efficiently calculates the shortest possible travel distance from every single point in the graph to the finish line. We then store all these values, which basically creates a distance map that we'll use to enforce our downhill-only rule. And what this does is pretty brilliant. The second we have this distance map, our graph is fundamentally changed. We can't just travel in any direction anymore. We can only move from a node with a higher distance value to one with a lower one. This basically puts up a bunch of one-way street signs all over our graph, which gets rid of all the cycles and transforms it into what's called a directed acyclic graph, or a DAG. Okay, on to our second tool. Now that we have our new one-way system, we need an efficient way to count the valid paths. And for this, we're going to use a depth first search, or DFS, and then we're going to supercharge it with a technique from dynamic programming called memoization. So here's how that works. We start exploring from our initial node. At every single step, we only move to a neighbor if our distance map says, yep, that's a valid downhill move. Now, the crucial part is this. Whenever we calculate the number of paths from a certain spot, we save that result. We memoize it. That way, if we ever end up at that same spot again through a different route, we don't have to recalculate everything. We just look up the answer we already found. It's so much more efficient. So we've got our key insight, we've got our two powerful tools. Now let's put all the pieces together and look at the complete, elegant master plan from start to finish. It's really a beautiful logical flow. First, we just set up our graph. Second, we run Dijkstra's backwards from the end to create our distance map. Third, with that map as our guide, we run our optimized DFS from the start to count all the valid downhill-only paths. And finally, we just return the total count. See how each step perfectly sets up the next one? It's awesome.
And what's the result of this elegant approach? Well, we get a highly efficient solution. The time it takes is mostly determined by Dijkstra's algorithm. That's O(E) log V, where E is the number of edges, or roads, and V is the number of vertices, or intersections. In plain English, it's really fast, even for big networks. This is no brute force hack. It's a professional, optimal solution.
So what does this all mean for you? Beyond just solving this one specific puzzle, there are some powerful, reusable strategies here that you can totally add to your own problem-solving playbook.
So what are the key patterns to remember? First off, if a problem's rules are based on distance, Dijkstra's algorithm should be screaming in your head. Second, always look for ways to use constraints to simplify the problem, just like how our rule turned a messy web into simple one-way streets. Third, combining graph traversal with dynamic programming is an absolute power move for optimization. And probably the most important one, sometimes the best way to figure out the first step is to start at the end.
And that's the thought I really want to leave you with today. This idea of reverse engineering a problem by starting at the goal is just an incredibly powerful way to think. So, my question for you is this. What other complex problems, maybe even stuff outside of programming, become surprisingly simple when you stop obsessing over the first step and instead you start by clearly defining the destination?